Welcome everybody. My name is Dr. Obeno. I'm a professor of hydraulics and hydrological engineering at Purdue University in the Lyle School of Civil Engineering. So this is the first lecture in a course named Wells Hydraulics. So this entire course will be about wells and how we extract groundwater for use. This is the second course in a 3 1-credit courses series. The first one was called Groundwater Cycle. If you didn't take it, I highly recommend that you bookmark it and go see some of the videos, because a lot of the content from this course, the Wells Hydraulics course, will rely on some background from the equations of flow that we introduced in the Groundwater Cycle course. The third module is called Contamination, and so it deals more with contamination of groundwater, landfill design, transport of substances that are in the groundwater, and this is again an independent 1-credit course that comes later. Okay, so for this specific course, the Wells Hydraulics, I will do a quick introduction on wells in general, what are wells, how they look like even, and then a couple of topics, general topics of interest around wells hydraulics, and then finally I will present the different chapters or sections that we'll go through during this course. So to begin with, you can find related topics or coverage of wells hydraulics in different books. I highly recommend the Fetter, the chapter 5 in Fetter. That's most of what we'll see in this course is covered there. The Charbonneau book is a very good book as well, and the third chapter in his groundwater book is dedicated to wells hydraulics, and it's a little more advanced than the Fetter, and so I also use some of that content during this course. The other books are just classic books. Some of them, especially the Bear, is a bit more advanced than most of the material we do here, but if you're really interested in groundwater hydraulics, I highly recommend the Bear. This is a very complete compendium of knowledge on groundwater. Dr. Bear also has some very good online resources that you can find. So if you go check his website, and you have a lot of examples and again pretty advanced topics on hydraulics, on groundwater. Okay, so I'll start this introduction with again here you have like two pictures, right? Two different pictures of wells. On the right hand side here some art, and then on the left hand side the Nazca Peru. So you might know Nazca as the lines, those lines that are visible from the space, and they've fascinated research during the 20th century about where they came from, what civilizations left them, etc. And one of the salient features there is those wells that are, you can see here, built in stones, and they're basically spiral staircase, if you will, spiral way to go down the hole to the water table. I'll show more example of wells basically in the next few slides. So here, if you're from Europe, for example, right, like I am, obviously I'm French, as you can probably tell by my accent and name. This is, for me, that's what a well looks like. So for me, a well, when I think of a well, that's that's the picture I have in my mind. And depending on where you're from, you probably have a different, or you may have a different image. So these would be, the typical public water wells that you would find in villages in France, in the 19th century and even before, where people would go and fetch water for their use. Obviously, before there was distribution, right, water distribution. So that would be typically a public well where people would go and get the water. So open pit well. Now, if you're in America, so here I'm talking to you from West Lafayette in Indiana, in the middle, the heartland of America. And here in America, a lot of people that don't live on a distribution network, so in a city, people living on land, farms, etc., they usually have their own individual well to provide their water for their house. And typically that's what they look like. So here on the right hand side, you can see all you see above ground basically is that little 6-inch pipe sticking out with a cap. And basically all the pumps and everything is inside that 6-inch casing. And that's a typical well, and that's a lot of what we'll talk about today will sort of refer to those sorts of wells. Obviously they can have different diameters, different organizations, but that's a typical, well here in America. When we think of a well here, that's probably what you think about. And then on the left-hand side, of course, is how we drill them. So it's basically a big truck with a big drill, literally like drilling down and down and down until it finds water. Other examples of wells. So this is, again, on the left-hand side here, an open pit, large open pit well. So, similar to the ones I showed you for Europe, but this is just a bit larger, and you can see the pulley system here to go fetch the water at the bottom. A couple of, or a topic of interest here for the wells that will be in your notes, in the intro notes. You can see here that mostly women fetch water, and so across the world, and I talked about it in the groundwater cycle or in the groundwater resources, first lectures in the previous module, but a topic of interest around, the water is that, well, the main thing about water is that it's heavy. So water is heavy, so you have to spend energy basically to move it around, and yet we need it. So when you don't have, mechanical systems, so pumps and, motors or energy like electricity, fuel, the energy we use is literally muscle. And typically around the world, women and children are doing that work. So a lot of the the world workforce is actually spent fetching water from wells. So you can see here on the left-hand side that, this is typically an all-woman assembly, around the well. So a lot of also social impact, of fetching the water. On the right-hand side here, you can see again, women and children. So children in this case, this is in Zambia. And you can see the well here is a borehole, so more similar to what an American well might look like, but here there's a hand pump, right, hand crank pump, so you can actually go fetch water there. Other types of wells that you won't find, I guess, nowadays in use, but from history. So here in Portugal on the left-hand side, and in Italy on the right-hand side. So you can see crossing 10 century, millennia, basically apart. So the left-hand side one is from the 5th century, right, of our era. And again, you can see that idea of a spiral staircase basically going down to wherever the water table is. And you can see here that's a really deep well. That's many floors, before you get to the water. On the right-hand side, same thing in Orvieto, Italy. But now we're talking about, circa 1500, so 16th century. But a very similar construction, right? The similar type of well. Again, those wells wouldn't be in use today, and actually their use for fetching water is debated. I mean, they obviously might have had a function of, providing water to a community, but they're also, designed so we don't know if there were some more spiritual, basically, activity, because these constructions are, gigantic. Finally, in what I call popular culture, but, let's say arts in general. So again, fetching water, it was such a fundamental part of existence all the way up to the 20th century, basically, or even the mid-20th century, that has been depicted, right, in culture for centuries and centuries. So this is just a couple of example, again, of European artists. So you can see those, on the right-hand side, the open pit well, and then on the left-hand side, a lady with a bucket fetching the water. And again, the topic of ladies and children fetching the water, that's pretty typical across cultures and times. Now, a few topics of interest around wells hydraulics. So this is a very well-known map of the water fountains in London at the end of the 19th century. So this will link a little bit to my third course on contamination, because this is a very famous one of the first, contamination stories that we know of, the John Snow map, linked to the cholera outbreak. So at the end of the 19th century, in many places, especially in the cities that were getting bigger with the Industrial Revolution in Western Europe, or even in America, the cities were growing fast, like Chicago, for example, has famous stories of contamination. So the problem is people were using water to drink, obviously, but they were also contaminating it with their own waste, right? There wasn't really a wastewater, way of getting rid of the water. So the wastewater from cooking and bodily functions were basically released in the street and typically contaminating the sources of water, obviously. So there wasn't really a recycling problem. So John Snow actually established this map. So the fountain, the main fountain was somewhere in the middle here in Broad Street Fountain. And you can see that around those little, the little squares here are the cases of cholera. So all those little black squares are basically the number of cases, in a household. And you can see that from the fountain, so from the fountain in the middle, there's basically a circle of contamination. So he was able to find basically the source of cholera and link the cholera outbreak to the water fountain and basically a waterborne disease. So really an interesting first map. We'll talk about this a little more in that third contamination course. Again, problems of water quality. So here in the US, the problem of fracking has become prevalent. There's a lot of fracking used to extract hydrocarbons for energy. And this is, big topic of, how groundwater can become contaminated from industrial usage, basically, or from industrial activity. Here in the Midwest, another big topic is fertilizer, for example. We grow a lot of corn and soybean, but mostly corn. Use a lot of fertilizer to grow the corn, and then that fertilizer end up in the surface waters and groundwaters, and there's a lot of eutrophication and large-scale environmental problem, including dead zones in the Gulf of Mexico, but that's true pretty much everywhere there's large-scale agriculture. So the coastal waters get polluted, and then there's like fish kills, and the fishing industry gets impacted. So really large-scale water quality issues, basically. Now water quantity, right? So the second aspect, or the main aspect maybe, of wells hydraulics is extract water. So it's really a problem of water quantity. How much can we use? If the quality is good, then then really the problem for wells hydraulics specifically is really a question of quantity, right? And here are a couple examples. So this first example is a paper in Nature Geoscience, and called Depletion and Response of Deep Groundwater to Climate-Induced Pumping Variability, right? So the idea behind that paper was, if you have a drier climate, obviously you need more water for the crops or for the usage that you have, so then you'll pump more, right? So if you have wells that tap into groundwater, then you can just crank them up and pump more because the climate is drier. And this is just an example map, right, where the groundwater level trends, linked to pumping are illustrated. Other topics are, more of the engineering type here. So dewatering. So wells are used to dewater. If you have a construction site and you need to do a foundation, typically you need dewatering. I mean, depending on your site, obviously. But if you have groundwater seepage, or if you're near a river, here's an example in Chicago, where the whole Chicago River basically has been walled off, literally. And then you need dewatering, obviously, on the left-hand side here, so you can pour your foundation. So dewatering is a typical engineering use of wells, basically, or pumps. Finally, the pump and treat system. And again, we'll talk about dewatering and pump and treat towards the end of those lectures here in this module. But the pump and treat is another usage of wells, basically, where you pump water that has been contaminated. You decontaminate, so you clean it up in some above ground facility, typically. So you have something, to clean the water on the top, a water treatment facility. Once the water is clean, you either re-inject it, typically, or, so that's the pump, treat, and then the injection is either you release the clean water to the surface environment, to the surface, waterways, or you pump it back into the aquifer, depending on what you need. So again, we'll study some of those systems to see how they work, pretty much. Finally, a lot of this course is built around modeling. So we'll see how practically, on a computer, we actually represent aquifers, and we do the modeling of the groundwater and the well. So here are a couple examples. On the right-hand side is a commercial package that you can use that is basically from the USGS. So USGS has a package that's called MudFlow. That's the most well-known, if you will, finite difference model for groundwater, but it's not very user-friendly. So a lot of either companies or even free software are basically skins around that model. So you can just click on buttons and input some parameters that you need and then model groundwater flow. So this is an example of that that's put out by a company called Aquavio, and the software itself is called Groundwater Modeling Software, GMS. And this is just a quick example of a plume from a well. So you have basically a pollution here, a pumping well here, and you can see the impact of those on the potential line, on the flow, basically on how the aquifer behaves. And you can see here a plume of contamination going around the pumping well, so not affecting the well too much. On the bottom left here, you have a simple Excel example, and I'll use Excel a lot in this class to just do finite difference, very easily and hopefully easy to understand for you. So we'll use a lot of Excel implementation, if you will, of the mathematical models that we'll be describing for wells hydraulics. So we'll describe different situations, use some mathematical equations to describe them, and then show you how you can model those equations practically on a computer. And here are the different topics that we'll cover in this one credit course. So again, the welcome introduction we just did, and then we'll get to steady flow. So first thing is, if you have a pumping well, and it pumps forever at a steady flow rate, then what is the influence of that on the aquifer? And we'll typically deal with confined aquifer and unconfined aquifer separately. And again, if you don't remember what those are, I invite you to go back to the definitions in the previous course. But the unconfined aquifer are basically those surface aquifers that have contact with the atmosphere. So they're underground, but obviously they have a water table and they're not constrained. The confined aquifers are like typically deeper aquifer that are below some confining layer. So let's say a layer of clay on top, right? So this water is completely basically isolated from any surface activity, pretty much. Okay, so steady flow to well. So again, we'll do confined and unconfined, and then we'll do transient flow. So transient means obviously where there's change, where if you start pumping water in an aquifer at the beginning at least, right, there's a period where things are not at equilibrium. You just started pumping, so until some later time where you reach equilibrium, steady state, there's something going on that is unsteady, so transient. So that's what we'll study. And that's how we do aquifer tests. If you want to know how good your aquifer is to provide water, typically you do pumping tests, and these are really important. A big topic of this course, or a chunk of this course, will be dedicated to those pumping tests and different tests. So again, transient, confined flow. Then there's some leaky aquifers. These are in between, basically a completely confined and unconfined. So they have some leakage, some sources of water. And then finally, unconfined, transient, unconfined flow. We'll also discuss slug tests. So these are like basically cheap aquifer tests, and we'll cover them. We'll study the well fields. And again, these are basically the dewatering example that I gave before, right? You use a well field, so you use a bunch of wells basically to accomplish some task, and we'll see how they work. So the dewatering is an example, and then the pump and treat and the capture zone, so the pump and treat system we'll cover as well. Finally, we'll do a quick lecture on mud flow example. So all these topics I'll cover with my own codes basically, so depending on, mostly in Excel, a little bit in MATLAB maybe, just to show you how this is done. But at the end, I'll tie it all up with a mud flow example. Okay, I thank you, and I'll see you in the next video. Thank you.